Fine, it's recording. Okay, so we are left out with the wave shaping circuits which can be designed making use of clipper and clamper operations. And the other one that we need to discuss is the Zener and the Avalanche breakdown mechanisms in a bit more detail and understand the fundamental difference between the two. Well, uh, as you can check on your screen, the circuit that has been shown, that is a kind of a wave shaping circuit. Now, why wave shaping is very much important in circuit operations? Because through wave shaping operation, you can generate a new form of waveform as per your choice or as the application demands. Okay, like for example, though it's not like this in this case of clipper and clamper, but just to give you an example, like say you have like say you are having a sinusoidal waveform. It's very common. That is, you're having some input line frequency from which you're applying some kind of a signal from a signal source. Now you need to generate a triangular waveform. So what do you need to essentially do? So obviously you have to get into an idea of a wave shaping operation so that that sinusoidal waveform can be converted to a triangular waveform. Or let us say you need to get into an idea where you have to need the output to be of square waveform type, or a pulse waveform you need to generate. So the sinusoidal waveform has to be converted to a pulse waveform. So the wave shaping circuits which are really employed for the particular purpose are important in this context. Now, just to have a quick view of some of the wave shaping circuits as being given in the syllabus right now, are clipper and please mute your microphone. So clipper and clampers. Now, what does these circuits do mean? When we talk about clipper, it specifically indicates the fact that is you are clipping off the voltage at a certain level. That is, you are not allowing the voltage to exceed that particular level, let us say. You're clipping it off to a certain fixed level. Okay. Obviously beyond a certain reference when it comes into the operation. And the other case is that of a clamper, where the main essence is to design a circuit with a different DC level. What I mean to say is this, that is you're having, let us say you're having a signal with zero DC signal. Let us say a sinusoidal signal having the reference axis x-axis. So it means it's basically a zero DC signal. Now you want to convert that sinusoidal signal to a kind of a waveform where the DC level of the signal gets enhanced to some plus value or minus value. So depending on that, you can design making use of a positive clamper or a negative clamper. That is clamping or restoring to a different DC level apart from zero. That is about clamping operation. That is also having a very good application, obviously, because if you demand to have a DC level existence over and above the AC components, so obvious that clamping operations do play important role. Obviously, what I mean to say is this, these kind of operations do have its application when we talk about, for example, we have talked about the case of a rectifier, and that too with the help of filter circuits, that is making use of a capacitor. That idea of the rectifier, where we have utilized the idea of a capacitor for that particular purpose, and a constraint had been maintained over there. That constraint was that the value of C into R, time constant, should be very high. Okay. But the point is, in that segment of operation for the rectifier, we are having a level of discharging going on, but the discharge level is very low. When we're talking about a clamping circuit specifically, it's having a very similar kind of an idea. The discharging level is too low, or it indicates the value of R into C should be excessively high. So if you can maintain that kind of a circuit, so in that case, we can generate clamping circuits over there. So we'll get in the corresponding circuit. So first and foremost, the clipper circuit, as you can check on your screen, a simple clipper circuit has been shown where the input potential Vi is being applied to a resistor diode combination with a biasing supply VR over here, as you can check. Now, obviously, when should that diode conduct? The diode will have its conduction at the point when the value of Vi exceeds VR and the diode D becomes forward biased. Now, out here, if we make the assumption that the diode D is an ideal diode having zero voltage drop, that is VD is equal to 0, VD is equal to 0. If we assume so, then in that case, these statements are perfectly fine. That is, when the value of Vi exceeds VR, as being given over here, the diode becomes forward bias and the value of V0 is equal to, what happened? Value of V0 becomes equal to VR. However, when the value of Vi is less than VR, obviously the diode should be in the reverse bias condition and hence V0 should follow Vi, as being shown over here. V0 is following Vi. The same thing has been depicted in this diagram. The waveform nature has been shown as well as the transfer characteristics. The green line is the transfer characteristic and the input and output signals have been depicted over here in this graphical representation as well. Now, as you can check on your screen, when the value of Vi exceeds VR, when the value of Vi exceeds VR, then the output gets clipped at VR, right? A clipping. When the value of Vi exceeds VR, the output gets clipped at VR. So what you have is kind of an operation. Look at this part. Here the clipping operation is occurring. That is, V0 is following Vi across this blue line. I mean the bold blue line, not the dotted one, or the dashed one rather. So the bold blue line is indicating V0 is following Vi when the value of Vi is less than VR. The moment the value of Vi exceeds VR, we are into the green line, coincidence with this blue segment as being shown over here, this line. Sorry. This part I'm talking about. So it means a clipping has occurred at the level, reference level VR. And this upper dashed portion, as you can check on your screen, this part is clipped off, right? So as you have studied about transistors, you are studying about the AC signaling operation of transistors, okay, and single stage transistors and all. Over there, we have a very important point, which is of quite importance, is this, that you need to bias the transistor properly. Why is this biasing so important? Because when you feed in a signal, let us say you're having a common emitter amplifier, though it's having a common emitter amplifier. So when you're putting up a particular signal to that common emitter amplifier at the base, you're getting the output from the collector terminal with respect to the emitter. Now the fact is this, that in this particular process, if the input signal swing exceeds a certain level, because it's an amplifier, then it may happen to then it may lead to such a scenario that the output signal swing moves into the saturation zone or in the cutoff zone, output signal swing, owing to which the moment the level gets into the saturation zone or in the cutoff zone, you are going to experience a clipping. The output waveform will get clipped. So a similar kind of thing is going to happen practically when you exceed the level of signaling operation in a corresponding transistor. So it means that you have to be careful about what is the level of signal that you can apply to a common emitter amplifier, because the common emitter amplifier is the out of the three is going to give you the best form of amplification in all respect. Well, so the clipping kind of waveform we can also observe in the context of amplifiers as well over here. So this is the case for the scenario where we are having a positive clipping. Now, if we move down, let us say we take up another clipper circuit. So what is the difference between these two? Look at the orientation of the diode. Diode's anode is on the top, cathode at the bottom towards the battery, that is VR, DC potential VR. It is just the reverse in this case. The anode is towards the VR and the cathode is towards the top. So obviously the operation that we are expecting to have in this corresponding circuit should be the reverse. What does it mean? That is, when the value of Vi, it's clearly mentioned over here, and you can definitely understand from this diagram as well. When the value of Vi exceeds VR, the diode is reverse biased. Isn't that so? When the value of Vi exceeds VR, diode is reverse biased. And the value V0 is equal to Vi. That is, V0 follows Vi. However, when the value of Vi is less than Vr, diode becomes forward biased and V0 is equal to Vr because Vd is equal to 0. No voltage drop across the diode, assuming ideal diode. Now, if you want to depict this particular idea through the transfer characteristics as well as the corresponding waveform, the same has been depicted over here, which shows when the value of Vi exceeds the level Vr, then V0 is equal to Vi. So this is this particular 45-degree line in the transfer characteristics, and the same has been depicted over here through this bold line. Look at this brown bold line. Okay. And the segment, the dashed portion over here in the output signal, this portion indicates what? The segment where we are having the aspect of clipping, complete clipping operation. So V0 becomes equal to Vr at that zone, in that particular zone. That is, the output will be something like this. Something like this, the output will be. So likewise, you are having a negative clipping, meaning that reverse part is completely clipped off along with some portion from the positive half as well. That all depends on what is the corresponding DC potential that you're applying across the diode. In series with the diode. That is VR. So that is another kind of a clipping circuit or a wave shaping circuit, as you can check on your screen. The third form is definitely the combination of the two that we have taken up in the context of Clipper circuit 1 and Clipper circuit 2. Look at the assumption, two independent levels with the assumption that VR1 is less than VR2. Now, if you observe the waveforms, I hope you'd be able to understand the operation, how it goes through. One thing is for sure, when the value of Vi is in between VR1 and VR2, where VR1 happens to be the lower level and VR2 the upper level, V0 is equal to Vi. Because none of the diodes are in conduction phase when Vi is in between the two. However, when the value of Vi is less than VR1, then what will happen? D1 will conduct. And when the value of Vi is greater than VR2, then what will happen? D2 will conduct. And accordingly, we are going to observe at V0, VR1 and VR2 respectively. So the same has been depicted in this signal over here. Look at this clipped version. In between VR1 and VR2, when the value of Vi ranges, then you are going to have a transfer characteristic with slope equal to 1. And in the rest part of the segment, that particular segment is where that part of the segment is where V0 follows Vi in this transfer characteristic with a slope 1. And in the rest part of it is what? The lower portion is VR1 and the higher portion is VR2. So you are getting clipped operation. One clipped signal. So you are going to have a signal something like this. A clipped signal like this, then like this, like this, like this, like this, and likewise. You have to go through. So kind of a trapezoidal signal will have its existence. And that too having a good level of DC value because it's not at the reference x-axis. It's having a good DC level and it's a trapezoidal signal. If you want, you can pull down the corresponding DC level back to 0 and generate a pure trapezoidal kind of a signal. No, not trapezoidal, the nature of the signal is very much like that over there. So that is the case of another kind of a clipper circuit that we take into account. Okay. Now, coming on to the idea of clampers. Now, as I was talking about, what are the essential components? It's clearly mentioned on your screen. Essential components in this corresponding circuit happens to be a capacitor, a diode, and a resistive element. Now it depends. Now, the example that we are going to go through right now has completely disregarded the existence of a resistance. Okay. If you put up the resistance, the nature of the circuit operation will be very similar to the case of a rectifier with filter. Okay. Now, if you want to put up some additional DC shift, then you have to go for another DC supply for its operation. Now, as I was talking about, that the magnitude of R and C should be very high. This is a crucial requirement in the clamper scenario, so that the capacitor, once it charges off, okay, once it charges to the maximum value, it doesn't discharge. Now, when the value of R is excessively high, or in other words, R happens to be an open circuit, I'm talking about the load, R, factor R. When the factor R happens to be an open circuit, then what will happen? The capacitor will not discharge at all. And it remains fixed at some DC level to which it has got charge up to. Okay. in one particular cycle of this operation. Now to understand the same, we have to go through two different forms of clampers, negative clamper and positive clamper. So on the very next screen, we are having the idea of a negative clamping. Now what is the ultimate outcome of this operation? The top waveform on which I have ticked right now is having the DC level equal to 0. And what about the bottom waveform? It's having a DC level equals to minus 10 volts. When we're talking about the positive diode clamper, it is just like here you're having the DC level to be equal to 0 volts. Here the DC level is equal to plus 10 volts. That is, you're switching the DC level to some other value, which is definitely not a 0 value. So let's try to understand this particular circuit, the negative diode clamper. Well, though everything is clearly mentioned on the screen, I hope it's not difficult to follow what is being given over here. But still, let's have a quick review what is being designed out here. So let us say that is when we are into the positive half cycle. When in the positive half cycle, what will really happen? And look, the diode is not having any kind of a biasing supply over here. I mean, series, there is no, I should not say like that. I should put it like this, that there is no DC source which is in series with this corresponding diode. So the entire output voltage is coming across the diode. So once the diode is in conduction, it means V0 should be equal to 0. Once the diode is in conduction, it means V0 is equal to 0. And when the diode is in non-conduction phase, it means that it should employ the idea of these two in a loop, Vi and Vc. So to get into that idea, let's have a quick example as being shown. That is, let us say the input signal, it switches back and forth in between plus minus 10 volts as being shown over here, right? Now, in the positive half cycle, when the capacitor is charging, what will happen? Now, what will happen? When the capacitor is charging, definitely till the point when it attains, 10 volts, the diode will in the conduction phase. And when the diode is in the conduction phase, the value of V0 is equal to 0. So till time point T1, the value of V0 is equal to 0. Till time point T0, right? Now what will happen beyond T1? That is the point of concern. Now what will happen? Now obviously, once the Vi gets to the value of plus 10 volts, now what is happening? According to the current flow, which has charged up the corresponding capacitor, what is the polarity of the capacitor? The polarity capacitor has been shown by the corresponding plus minus notations, which has been shown on the screen over there. So therefore, now when the value of Vi falls below 10 volts, what would really happen? Now, what is the value of Vd? What is the value of Vd if I take up this particular loop? So let us say you're having over here minus plus because it's acting like a supply. So it should be equal to Vi minus Vc. Simple. Vi minus Vc. So that has been mentioned.
Yes,
over
sir.
here. Vi minus Vc. Now, when the value of Vi becomes say equal to 9 volts, what would happen? When the value of Vi is equal to 9 volts, that is, it has just fallen off from the corresponding peak, and the peak value is 10 volts, has been shown over here. Peak is 10. So when the value of Vi falls below 10 volts, let us say we take up a value, for example, 9 volts, what would really happen? 9 minus 10. So when it is 1 minus 10, it means minus 1. So when we are having minus 1 volt, that minus 1 volt is not going to put the diode into the conduction phase. So minus 1 volt means what? The diode is open. V0 will follow the input cycle. So V0 should be equal to minus 1. Very obvious. Diode is off. Diode is open. So obviously V0 should be equal to minus 1. So when the value is equal to 8, then it is 8 minus 10. So minus 2. Likewise to 0, when it will be equal to minus 10. And when you're having to the negative half cycle completely, till this particular point, you are going to have the value equal to minus 20. And likewise, it will again increase. So the nature of the waveform that we're going to observe at the output, V0, would be the one which has been shown at the bottom, which indicates that is the DC level of the signal, which was initially at 0 volts, over here is no more at 0 volts. It has been clamped or restored to a level less than 0 volts in this symmetrical context of this example, approximately at minus 10 volts. So the DC level for this signal is at approximately minus 10 volts. So that is the final outcome that we observe. So this is the case of a negative diode clamper, because you are clamping the value to a negative level, and that is that to minus 10. So that's an example of a negative diode clamper. Now if I take a positive diode clamper, look at the difference. Here the
Sir,
diode, yeah,
sir, I have one doubt.
yeah, yes.
Sir, in that example, we said that
Sorry.
EI minus VC, and you
Mhm.
said that 8 minus 10, 9 minus 10. Is that VC value 10 is fixed at the peak?
That okay, right. Good point. I didn't. I simply skipped off that particular point. Thank you for notifying. Actually, now what is going to happen? Look at the factor C. What did I mention in the earlier screen? That is the magnitude of R into C is going to denote the time constant of the circuit. So when you are going to have a discharge of the capacitor discharges with the time constant tau equals to RC, R into C. And the equation is e to the power minus t by tau with some initial potential, say V, sorry, with some initial potential V from where it starts off, the initial potential, it starts discharging. And the discharging time constant is tau. And this tau is equal to R into C. Now, if we can put the value of R to be very high, ideally in this case, there is no R. There is simply no R through which the capacitor can discharge. So if there is no R through which the capacitor would be able to discharge, look at the polarity of the capacitor, and then you get into this thought. So there is no R through which the capacitor can discharge. So as there is no R, it means the time constant is infinite. So when the time constant is uh, assumed to be equal to infinity or very high value, so the capacitor is obvious that the capacitor will hold the voltage to which it has been charged up to. That is the peak value 10 volts. So it will hold the 10 volts DC voltage. That is why it's clearly mentioned over here that since the capacitor is holding its charge in this particular point, capacitor is holding its charge, it behaves as a DC voltage source while the diode appears as an open circuit. Because the vector R is not existent or open, in other words. I should not say not existent. It is more appropriate to say factor R is open in this circuit operation. It is very much ideal kind of a scenario. We have simply disregarded R. You think about that, there was a case of an R when we talked about the filter operations in rectifiers. Otherwise, how can we have the discharge? We need to have a discharge. The discharging operation is very essential out there in the filtering scenario. Okay. If you do not have any discharge, in that case, it means what? It will have the value fixed at the corresponding capacity potential. Okay. Now, according to the circuit design, rather I should rather put it like this, because the output voltage is being observed across the diode. That is why we are having a kind of a clamping operation out here. We are not having the output voltage across the capacitor. We are having the output voltage across the diode. And hence we are justifying the corresponding clamping operation. When it is across the capacitor, then in that case, we can design a filter kind of an issue. Here, the output voltage across the diode. So it's a case of a clamper. Now, the reverse part of it is definitely the positive diode clamper. How is this different? The diode orientation is just the reverse. Orientation is just the reverse. I don't think this needs any explanation, because just to have a quick view, when the diode should conduct, when we have this notation for the polarity at the input, minus at the top, plus at the bottom. So we are talking about the reverse half cycle of the input waveform. So when we talk about the reverse half cycle of the input waveform, the diode will be in the conduction phase as long as the capacitor C gets charged up to 10 volts, as being shown, with the polarity depicted clearly for the capacitor. And the information is also shown in these two diagrams. Look at this fact. It is just the reverse. Whatever I mentioned in the earlier case, it is simply the reverse of it. The idea is same. We are having the same idea, according to which we are getting it. Yeah. Do you have any question, anyone? Okay. So The idea is just the same. That is, as long as it's not attaining the minus 10 minus 10 volts, the diode is in conduction as being shown. Excuse me once. Sorry for the interruption. So we are having, so the idea is VD is equals to VI minus VC out here. So here also the same idea, that is when we are having till minus 10 volts, the diode will be in conduction, and at the output we are not going to observe anything. So at the output, we are going to observe a potential which will follow the input cycle. And I should not say follow the input cycle, the corresponding, according to the KVL principle of VI minus VC, whatever outcome will come up, that will get reflected across V0. True. And the outcome will be the one as being shown over here. It is just the reverse. And whatever way we have calculated in the earlier case, in the similar way, if we calculate, we will have 1 volt, 2 volts, 3 volts, 10 volts, and to the peak 20 volts. Again, you come down, and likewise the circuit operation gets into the picture. So in this case, we can design a positive diode clamper. Again, I repeat that the output voltage is across the diode, not across the capacitor. Hence, it is a clamper circuit. Okay. So this more or less clarifies the wave shaping operations in the corresponding context. Now, in your exams, you may be given a question which can be like something like, you may be asked about a clipping circuit where it employs the idea of a Zener diode along with a normal diode. You have the concept of what a Zener diode is, the Zener regulation and all. So keeping all that thing in all those aspects in mind, you are having a normal diode and a Zener diode. What I mean to say is this: it is, let us say, instead of these two diodes, normal diodes, if I put it up as Zener diodes, what will happen? Or let us say we put up two diodes in series to one another, and both the diodes are Zener diodes. Instead of putting up this VR1, I simply remove this segment. I simply remove this part. Okay. I put up two diodes in series, D1 and D2, where D1 say is one Zener diode and D2 is another Zener diode, but they are having a back-to-back connection, reverse mode connection. You check what the output is. The output will give you the idea of a clipping circuit only. So likewise, you can understand how it really works through, okay, for the clipping case and over there. Next is the context of this Zener and Avalanche.
Sir, last doubt, one doubt, sir.
Yeah.
Sir, next slide, the last one.
Sure. Yeah.
Yes, sir. By taking the reference of the input wave, we are doing some modifications in output. That means we are deciding whether it is at the peak, what happening. But how can I draw the input signal, sir? By giving when it is given the circuit in the question.
No. Probably I didn't get your question, but whatever I understood, let me try to frame an answer based on that.
Sir, my question is, in the problem when it is giving the circuit diagram, how can I draw the signal, that is input signal wave, with the reference of that? Yes, yes.
No. That is not a. Oh, I got it. Well, that is too. The point is this, that you are having the corresponding circuit over here, and let us say on a breadboard, you have made a connectivity based on the connections which have been shown for this positive diode clamper, for example, and you are observing the output, okay, on the breadboard across the diode. That is your intention, the one which has been depicted on the screen right now. And the signal source is this one. Now the point is this, that when will the diode be in the conduction phase? Obviously in the reverse half cycle, not in the forward half cycle. Now the case which has been shown in this context, now look, forget about this segment. Maybe you are having a confusion about this idea. Forget about the the conduction of the diode, and hence no output in between 0 to T1. Simply forget about the conduction of the diode and output voltage to be equal to 0 in between 0 to T1 in the negative diode clamper or in the case of the positive diode clamper. Because this is simply a case which depicts the conduction of the diode. Otherwise, the diode is not going to conduct any time, at any point of time. It will be in the non-conduction phase only. The moment it comes under conduction, it will get into the concept of a zero output. is not in getting into that particular conduction and that particular stage. So the point is, this is just a general outcome. You are having a waveform, sinusoidal waveform. Maybe you are having a confusion like in this case, we are starting off from the positive polarity. In this case, we are starting off from a negative polarity. That may be a
Yes, sir.
confusion to you.
Yes,
But
sir.
the thing is this is just a general context. Why we are putting up like this, why we have shown like a negative polarity and accordingly this diagram has been taken into consideration, just to make you understand how come we can end up in this general waveform and the output of V naught has been shown over here. How do you end up in that kind of a waveform? Forget about the conduction phase of the diode, because that is a very insignificant period. According to this particular circuit, when there is no resistor, when there is no question of having any resistor, in that case, the conduction phase of the diode and hence no output across the diode in between 0 to T1, this is insignificant. The significant portion is beyond T1, where the entire waveform shifts upwards in positive clamping and it shifts downwards in negative clamping. Think in that
Okay.
strategy. Okay.
Yes, sir. Okay.
Just disregard the fact that is in this case I have shown, just to make you understand how it really works. It has been shown something like this. Think from a general point of view. Okay. General is this one has been shown. The blue line which has been shown at the bottom. Forget about the non-conduction of the diode segment. That is definitely going to occur, but that time is insignificant. Okay. Because it's just a small portion, just one quarter, just one quarter of a waveform. So obviously it can be neglected safely. So now let's move on to the Zener and Avalanche context. So we are the final thing that we need to discuss. It will be a small discussion just to have the understand difference between the two cases of Zener and Avalanche. As you know one thing very well, that Zener breakdown does occur at low voltage, lower reverse bias voltages compared to avalanche breakdown. Please mute your microphone. Yeah. So the Zener breakdown occurs at lower voltages, reverse bias voltages compared to the avalanche context. Now to have that idea realizable, please mute your microphone. Otherwise, it's difficult for me to conduct the session.
हार्ट म्यूट कर लो हार्ट.
Otherwise, I will mute every one of you. All will be muted instantly. You please mute your microphone. Thank you. So we are depicting Zener and Avalanche. Now the fact is, what are the salient requirements for the Zener diode and the normal diode? I think I have to mute everyone. Should I mute everyone or leave the session? What do you want? You please mute your microphone. I'm telling you.
Sir,
Please mute your microphone.
Please not muting it, sir. He is not muting it.
Sir,
Sir, please mute hearts.
yes, sir. Kindly mute everyone.
You can mute Hearts if you want. I think he's unmuted by mistake.
Please mute your microphone.
Sir, type mute on. Sir, click the mute on option on the chest.
Harsh is not listening.
Good. Yeah. So, when we are talking about the two different kinds of diodes, what are the salient requirements in the corresponding cases? So, when we are talking about a Zener diode, the salient requirements have been clearly mentioned on the screen. That is very high doping on both sides of the junction. When we are having a PN junction diode, but there should be very high doping on both sides of the junction. So that is of the order of what we should normally say. It is of the order of, let us say, 10 to the power of 17 or 10 to the power 18 of that particular order when we have the doping concentration. In that context, we can put it up as a Zener diode. Okay, above 10 to the power 15 at least. Okay. So very high doping is an essential constant on both sides of the junction. And the second thing is this, field ionization gets realized in Zener. However, when we talk about the Zener context, it is either moderately doped for both the sides of the junction, or one side of the junction is low doped or moderately doped and the other side may be very highly doped. I repeat my statement. In the Zener case, both the sides of the junction should be very highly doped. That is an essential requirement. In Avalanche case, both the sides of the junction should be low doped or normal moderate doped like a normal diode, okay? Or at least one side should be moderately doped and the other side can be highly doped, because the essential breakdown potential, if we get into the analysis, though we are not going to show that analysis in detail, if we get into the analysis, we can do understand the fact that is the breakdown potential will essentially get guided by the moderately doped segment, not the highly doped segment, okay, in the Avalanche context. Now, as you can check on your screen, you must have studied about these corresponding band diagrams. Now, the bending of band diagrams have been shown. So this side is your P side of the junction and this is the N side of the junction, right? Now, to maintain the uniformity of the Fermi level in the corresponding scenario, there is a bending of the junction, bending of the corresponding conduction band and valence band at the corresponding junctions when we are having a PN junction device. EF is the corresponding Fermi level in this particular context. The one which has been quoted over here, this particular diagram, band diagram, this indicates the PN junction diode is under equilibrium. Or we should put it like this, that is, a PN junction diode is having no biasing, neither forward nor reverse. There is no biasing in this corresponding PN junction diode. Now, this picture is similar for the case of a normal diode as well, exactly similar for the case of a normal diode. But when we take into account the Zener breakdown, and that too, when we get into the idea of the reverse potential application, then the transport phenomenon of the carriers becomes different. In the context of normal diodes, we have the idea of avalanche breakdown, which we are going to discuss a bit later. And in the case of Zener diodes, the case that is happening has been shown on the right in this particular context. So what is the case? You know that Q is the electronic charge. Let us say VR happens to be the reverse potential. So the amount of energy change when we're applying a reverse biasing potential across the diode equal to VR, amount of energy change is equal to Q into VR, E equals to QV. And that energy change is going to be depicted in what sense? In the sense like this. One thing we know very well, that when we're talking about reverse bias application, it means that is the N side positive potential is higher compared to the P side. N side's positive potential is higher compared to the P side when we talk about VR is negative or reverse bias potential. In other words, it means in the electronic energy level context, when we apply the VR potential, the energy band will get shifted on the P side with respect to N. In other words, it means what? That is, the electronic energy band diagram on the P side will shift upwards with respect to P. Or in other words, what we can say is that is the electronic energy band diagram on the N side will move downwards. Either N will move downwards, we can think in this particular way, or the energy band diagram on the P side will move upwards, because the potential on the N side is higher compared to the potential on the P side for reverse biasing. And owing to which, what is going to happen is the point of concern. Now, Fermi level is close to the conduction band in the N scenario, and it is close to the valence band in the P scenario, as you can check on your screen. This is fundamental concept of Fermi level. So from here we can depict one important conclusion, that the holes in the existence on the P side towards the valence band are close to the valence band edge, EVP, on the P side. The electrons which are existent in the higher energy states, obviously in the conduction band I'm talking about on the N side, they are close to this ECN, very close to ECN. What does it really mean, therefore? It means that the higher energy states electronic energy states in the conduction band edge towards the N side, most of the states remain vacant. Similarly, the lower energy states on the P side below the valence band, as we move deeper, as I have shown in the lower direction, as we move deeper into the corresponding valence band energy band diagram, it means more number of filled states are present. Holes are present close to the valence band edge of the P segment. Now, if the VR is applied and the energy band diagram has got a change of Q into VR as been shown on the screen, what will effectively happen? The P side will get lifted in energy band with respect to N. Owing to which the outcome is this, that because of having very high doping, I will just talk about the physical aspect, not mathematical aspects or any further things over here. Owing to which what will happen, that is, because of this very high doping on both the sides of the junction, the depletion width at the junction is extremely low. It's very thin. Depletion width is very thin. And the corresponding carriers, I should rather force on the fact that is obviously the electrons. Because when we talk about the reverse biasing case, electric field is in which direction? Electric field is in this particular direction. Okay. So under the action of this corresponding electric field, what would really happen? The electrons from the P side will gain sufficient amount of energy through which it can simply punch through the corresponding thin barrier or depletion region and move towards the N side. In other words, it means that is the filled states on the P side are exactly opposite to the empty states on the N side. And easily from the filled states, it tears off, punches to the barrier and moves onto the N side and occupies a position over there. It gets some energy. So it means sufficient amount of energy it can have from that corresponding electric field. The approximate level of electric field which develops to generate this effect into concern is of the order of 10 to the power of 6 volts per centimeter, or even higher than that. 10 to the power of 6 volts per centimeter electric field I'm talking about. If that level of electric field gets developed across that thin depletion region, then we can have the concept of tunneling. We can have the concept of tunneling. We do not need to get into the idea of, now look, one thing I would like to mention, that under reverse biasing, two kinds of transport phenomenon can happen. One is either you have to surpass the hill or the potential barrier, through which very less amount of electrons do participate, as we all know, under lower potentials. And the other one is, that is the one which we know under the case of classical mechanics. And the other one is the idea of quantum mechanics, through which we have quantum means particle. So particle mechanics, quantum mechanics, in that particular case, when we talk about particle mechanics, we need to get into the idea of a wave function of a particle. And hence, we need to understand the particle's movement utilizing the Schrodinger wave function. It's not as simple as the case when we talk about the barrier potentials, the surpassing the barrier potential, moving on to the other side. In that case, we do not need to understand the essence of the Schrodinger equation. So the wave function and all these concepts do have its effect over here. And it's completely a segment on which comes under device physics. Okay. So through which what we have is this electron tunneling does happen, and accordingly, the current transfer has its effect from N to P. Well, now as this electric field is capable enough to break the covalent bonds on the P side, because field energy states are over here, it's breaking off the covalent bonds, making the electrons free, punching it through the barrier and moving on to the other segment, that is towards the N side. So this idea is called field ionization. This idea is called field ionization. So these are the two salient requirements in the context of a Zener breakdown, when we talk about Zener breakdown. However, when we think about avalanche breakdown, what is the scenario? Obviously, electric field should be in this direction only because it is under reverse bias. What does happen? What happens is this, that here we do have the idea of impact ionization, not field ionization. Now the question is, what is this impact ionization all about? Now, let me give you an example. If you think about normal diodes. Normal diode, not a Zener diode. Normal diodes do have avalanche breakdown more or less above 8 volts. Not very limited diodes have avalanche breakdown less than 8 volts. To be very much frank with all of you, if you are encountering in any kind of a diode a breakdown potential, let us say you are applying the reverse biasing voltage and you are observing the corresponding current flow to the circuit. And what you observe is something like this, that is the breakdown potential is in between say 5 to 8 volts. The breakdown potential is in between 5 to 8 volts or around 6 volts or 6.5 volts, something like that. Though we quote it to be a Zener breakdown because Zener breakdown has its primary effect over there, but in essence, that is also part of device physics, it is having a combination of the two. Below 8 volts, whenever you are having a kind of a breakdown, it is a combination of Zener with avalanche. I mean, what I mean to say, avalanche is slowly trying to get into the picture. Zener is dominating. Till 8 volts, Zener will dominate. Beyond 8 volts, Zener has got no information. Obviously, the breakdown, if it happens to beyond 8 volts for any kind of a diode, definitely it is not a Zener diode for sure. Any kind of a Zener diode has got breakdown potential lower than 8 volts. Okay. Now, and the avalanche breakdown is for sure if the breakdown potential is above 8 volts, approximately. I'm talking about from the point of view of mainly silicon diodes, to be very frank with you. Now, as I was talking about this impact ionization, what does happen out here? The electric field which develops in the depletion region, what should it do? It will simply accelerate the carriers towards the N side. That is, the electrons on the P side will simply get accelerated towards the N side. I mean, once it gets into the corresponding depletion zone, it can acquire sufficient amount of velocity followed by kinetic energy, which helps it to traverse the depletion zone. Once it is able to enter the corresponding depletion width, the electron, look, I should repeat that there are no carriers in the depletion zone, but under reverse bias, if obviously some carrier flow is flowing, is definitely existent over there. Otherwise, how can the current get realized? Isn't that so? So it means the moment a few carriers are able to get into the idea of the depletion zone, and the electric field is very much existent in the corresponding depletion zone, the factor E, as I've been shown over here, the factor E. So what will happen is this, it can gain that much, a huge amount of kinetic energy from the velocity as well, and that will be sufficient enough for it to traverse through the depletion zone. Now this energy, when it traverses through the depletion zone, what does really happen? This energy is sufficient enough to bombard the atoms, the neutral atoms present in the depletion zone. And what is the effect of this bombardment? The electrons become free. And it creates an electron-hole pair in the energy band diagram. I mean, holes are created in the valence band with electrons in the conduction band. So it means what? That is, that level of kinetic energy gets developed by the corresponding carrier, which is essential for a carrier to get to be torn off from its own covalent bond and put it to the corresponding conduction band, surpassing the forbidden energy. You know that is in between valence band and conduction band, the corresponding energy is called the forbidden energy. This segment is called the forbidden gap. So the forbidden gap's energy higher than that, plus the amount of energy which is required to tear off the electrons from the covalent bonds, even if higher, that much amount of energy gets developed across the junction within the depletion zone. And due to which, what happens is this, the electrons and holes, secondary generation of electrons and holes do happen. Those secondary pairs, electron hole pair, EHP, those secondary hole pairs
Hello,
are
sir.
going to, yes?
So my 90% data was used.
You can leave, not an issue. So when we are talking about, so the secondary electron hole pairs, they are going to bombard with further neutral atoms present in the corresponding depletion zone. owing to which, what does happen? Owing to which what happens is this, it can generate tertiary carriers. And all those electron hole pairs will move in the opposite directions. And accordingly, the current conduction has its effect in the avalanche scenario. Now, when this number participation of these carriers, that is the electron hole pairs, becomes excessively high, then in that case, we have the concept of breakdown. Right? And that happens higher than 8 volts for the case of silicon PN junction diodes, which are moderately doped on both the sides, or at least one side is moderately doped, other can be very highly doped. So this aspect through which it is bombarding and creating an electron hole pair, this idea is called impact ionization. So this is the idea of impact ionization through which the avalanche breakdown does have its effect in the corresponding process. Okay. I'm not getting too much farther into the discussion to the mathematical equations through which we can definitely understand, that is, how to get into an idea from where we can have the concept that is, and what I have mentioned is, that is, let us say a Zener diode, let us say any diode, forget about whether it is Zener or Avalanche, what is happening. Now, you know that is this much amount of electric field is getting developed across the diode. You are developing that concept, okay? You know the doping concentrations. You know the values of the electronic charges, the permittivity of the medium and everything you know, right? The contact potential, everything is known. You're just required to understand what is the potential at which the breakdown is really happening. It is possible to find out. It is possible to find out the corresponding breakdown potential. In that particular process, if the breakdown potential happens to be lower, given all the parameters, there is an equation for it. If the breakdown process happens, the breakdown potential happens to be lower, then you are assured of the fact mathematically that it's a Zener diode. You don't need to understand that how this thing is going on, but you can directly get into the idea that, okay, this is a Zener diode. You know what is the electric field, you know what are the dopant concentrations, that is sufficient. You can understand from the value that, okay, this is a Zener diode from the mathematical equation. Similarly, you can also understand this is the avalanche breakdown, avalanche diode, a normal diode. And likewise, it can be gone through. So that's all from this segment of Zener and Avalanche. I do not think anything else is required. I thought of covering the mathematical equations, but unnecessary, it should stress you a lot, and it's not relevant as well. It needs some more points to be discussed. I don't think that has been discussed earlier. Electric field intricacies and the depletion zone, mathematical equations. I don't know how far it has been discussed, but it has got some more intricacies which we need to go through. Unless and until we don't go to that particular part, we won't be able to understand the concept which I right now quoted. That is understanding the breakdown potential from the electric field and the dopant concentrations. So that's all. Now, if you have any question, you can raise your queries. Maybe, yeah. Anyone is having any question? Okay then, so if you're not having any queries, so I will simply take your attendance and we leave today. Just a minute.
Sir, clamper part. Sir, can you send the clamper and flipper part PDF to group MS Teams?
Just a minute, is it not uploaded?
Yes, sir. Yes, sir.
I think it is uploaded. Clipper, clamper,
No,
clamper.
sir.
No, sorry, no. I don't think I'm wrong. I think clipper and clamper is not yet uploaded. Maybe.
So then please upload it.
It is not uploaded. I have to check it once. I think it's not uploaded because just the rectifier and regulator segment is uploaded in my part.
Yes, sir. I.
True. I will upload it. No need to worry.
Are the results of C1 declared, sir?
No, not yet.
Okay.
Results of C1 not yet declared.
Sir, for this part, on which book we have to refer for the numericals and all?
Look, the numericals, there are lots of numericals given in Boylsted. There are other numericals given in the...
give a...
And there are multiple books. All books are having numericals. If you stress on this aspect of basic electronics, a number of multiple books are there. You can refer any book.
Can you upload a genuine book in the MS Teams or somewhere else?
Boylsted, I have to check whether I am having an e-copy of Boylsted or not. Else, if anyone is having, please share it with the entire class. I think in the last class I was
Yes, sir.
somebody was saying that he or she is having this particular material. So if it is possible, share it, or else I will check whether this book Boylston Nasinski is there, an e-copy is there or not, and accordingly I will share it. I will check my repository once. Okay. Yes. Any question?
Sir, how is VK Mehta and Rohit Mehta electronics?
I didn't get your question. Can you please repeat?
Sir, how is VK Mehta and Rohit Mehta electronics?
Oh, VK Mehta. Okay. You're talking. VK Mehta, I think it's a problem oriented. There are lots of, I have gone through VK Mehta. Problems are there in VK Mehta. But I would like to say one thing. We are referring about books like Cedra Smith. Then we are referring about books like Boylston Nashelski. Now, these books, even if Milman Halkias, if I take, but though Milman Halkias is a bit difficult to understand. Okay, just a minute. Let me stop the recording. Oh no, let it be on. Let it be on. So these books are there, but I would like to say one thing, that is regarding VK Math and all. You please be when you are going through the various numericals. Okay, please go through it properly, solve those numericals yourselves, and tally with the answers given in the book. That is bit essential, because in some of those books there are some printing errors which probably you may get confused. Even if there are printing errors in the equations, forget about the calculations. Calculations outputs, there may be errors. That is a separate scenario. Sometimes in some of the ebooks, on some of the books rather I should say, some Indian publications, some of the books, there are printing errors in the equations itself, conceptual equations which have been applied for solving the particular numerical. So that you have to be careful about. In VK Math, I don't think there is any mistake. Still, please check once.
Sir, one request, sir.
Sure.
Sir, we got that Boylston and that book, but can we get the solution manual also, sir? Please.
I don't think.
Sir,
I don't think I am having the solution manual of Boylston manual.
Sir.
No, sir. Some of the textbooks it's given, sir, but
let me tell you, I have the book by Cedra and Smith, Microelectronics, and Cedra Smith's solution manual is there with me. This I have with me currently, and for the others I have to check, because these two I do have, which I know. I have to check for the others whether I'm having any solution manual or not. So that's all. If it is possible, you please try to download or solve the problems. I will check whether this national ski Boylston national ski is having any solution manual. Okay. If it is there, I will try to upload the same in MS Teams in my channel at least. Okay.
yes, sir. Please do it as.
I have to check it once. Okay. So if that is the end of the story, so I think I have downloaded the attendance. Yeah. So that okay then. Thank you.
Sir, I have a doubt.
You have a doubt. What is the doubt?
Sir. Does Tata MC Grahil electronic principle book is same as Malvino book?
Malvino Leach. Can you please name the book once again?
Yes, sir. Electronic Principles Tata MC Grahil edition. Malvino Electronic Principles by Tata MC Grahil.
Okay. Yeah. Malvino is there. Electronic Principles. I am having that book. I am not the e-copy, but the hardcover book is there with me.
Sir, is it enough for our preparation?
Look, for basic electronics, I think that is fine. From basic electronics, you can refer to all these books. All these books are equally good. I should rather stress on the fact, whatever has been covered in the class, theoretical discussions, you follow those context, whatever has been discussed. Based on that, it's better to answer. And regarding the numericals, the more and more textbooks you refer to, the more and more types of numericals will get exposed to. Different types of numericals you get exposed to. So there are various types of numericals which you can go through. Starting from diodes or transistors, because in your instance you are going to have numericals based on mainly these clippers. I mean the ideas which I have right now shared, with some obviously some values being kept into the input and the diodes with some potentials and something like that. For transistors also some circuit may be given with the the relevant capacity, the resistive values and all, context of biasing, something like this. So now what kind of problem is there? It all depends. So more and more books you refer to, you may encounter one or more different kind of problems. Okay. So Malvina is a good book. I know that. I'm having that book with me.
Okay, sir.
Okay. Okay then. So thank you. So we stop here. Stop the recording.
Thank you, sir.
Currently, just
Thank you, sir. Thank you, sir.
okay. You can leave. Not an issue at all. Thank you.
Thank you, sir.
Thank you, sir.
And so please
Thank you,
upload
sir.
the
Thank you, sir.
Sir,
It will
please
also-
share the solution, sir. Sadra Smith book, sir.
Cedra Smith is there with me. That I can send. Not an issue.
Solution.